All right, welcome to a lecture that is all about files. So we're going to learn how to write to them, read from them at like the lowest level, and like what's going on in the operating system when we talk to files. So I guess let's just get started. So at the lowest level, a file is a number. All right. So like when you have like a Mac, if you have a Unix machine or you have a Linux computer, the operating system, every time you open a file, is going to give your program an ID number that corresponds to the file. You're getting a special number called a file descriptor, all right? And that will reference the file from then on. It's just like, give me this ID number and I know that you mean this file that I've already opened for you, okay? So file operations are privileged things. They require some intervention from the operating system because it does not trust us, the programmers of our normal programs, all right? So yeah, file descriptors are FDs for short. Those are just like unique little ID numbers for like a file that you've opened, okay? Or something special that is similar to a file, like your keyboard, the terminal screen, which we've talked about already. So here's a little bit more about that. So every time you open your program, every time you run a program, it gets 3 special files opened for you by default, all right? With 3 special file descriptor numbers that are always these, and they're never used for anything else. All right, so file descriptor number 0, that is the user's keyboard. So that's standard in, which you can read from. It's not a real file, it's a fake file, but it acts a whole lot like one, doesn't it? So it's useful that you could use read to get from the keyboard, right? To get information. And file descriptor 1, that's standard out. That's another important one, right? If you write to that secret fake file, then it'll print stuff out to your terminal screen, which is really cool. And then same for file descriptor number 2, right? File descriptor number 2 references the standard error output, which is still output to your terminal. Standard error, but it's a different kind of output. It's meant for error messages, yeah. So those are some fake files, and there's other things that kind of act like files as well that you can open. But if you want to open a real file, it's going to work in the same way. So you actually know pretty much how to deal with all these things. Like if you open up, you want to like open file.txt or something, like a real actual file, then you're going to get back some random number again. It's not something hard-coded anymore. You'll get back some random number when you ask the operating system, hey, I want to open this file. It's like, okay, yeah, use this number when you're talking to me about it. All right? So that's kind of how it's going down at the deepest level. And so let's talk about syscalls, because kind of right? Standard out is the terminal screen, and so somebody deep down, when you're doing printf or when you're doing cout, they are making the right syscall to file descriptor number 1. Okay, that must be what happens. That's the only way to print to the terminal. Okay, so secret things are happening. Let's make it less secret. Okay, so here's how to use system calls to actually open a normal file with like a normal name. All right, so we actually have to open the thing, and then we can read from it or write to it and then close it. Okay, so yeah, all file operations are privileged operations, which means you need to go and ask nicely of the operating system, hey, can I please do this thing? Okay, so here's our stuff. Scrolling on down, you know that read and write, right? Those are like 63 and 64 or whatever. So there's read and write. You also have open at and close, all right? So maybe we'll have an example with opening, reading, and closing. And so open at is a special one. It used to just be there was an open syscall, but they deprecated it. That's not possible to do on ARM64, and so we're forced to use the fancier syscall. It's called open at, all right? And then here's the kinds of things it takes. It takes the name of the file you want to open. That's your path name, and then takes some other stuff too. Okay, so here's an example. Here's our first example. Let's use syscalls to count the number of A characters in a text file. All right, so we'll read every character in the file until EOF, and then we'll see what we get. All right, so we're going to have to open the file first with the open at syscall. And then here's what the other things mean. This is a directory file descriptor, which is a disgusting thing to teach. It's weird to think about. It's you give the name of the file that you want to open. You can either give it as an absolute path from like the root directory, like if you say pwd, for example, that's like this is an absolute path. It's like starting from / the root directory. Here is how you get here. So if you give that this dir file descriptor, directory file descriptor, does not matter. But if you give something relative, like, hey, I'll eventually make a file in this folder called like file.txt or whatever. If I just say open file.txt and give that as a string, it needs to be relative to something, and then this is what it's relative to. Do you want it to be relative to the current directory? Do you want it to be relative to some other directory? You can open a directory itself as a pretend file, okay? And that's what you give there. We're going to give a special constant called this that stands for the current directory. So we'll just give a name of a file without any qualifications, and it will open it up relative to our current directory, which is what you would usually expect. Okay, that's kind of how it works in C++. So that's the value we're going to give. I think it's like negative something, some secret value. And then it also takes some flags. Flags are like, how do you want to open the file? It's like a mode for which way you want to open it. Like 0, for example, means I'd like to open up the file for read only. I don't plan on writing to it. Read only, please. And yeah, there's other ways to open files too. So you can give something other than 0 here. And then there's a mode in addition to that, which is optional. But modes, we'll talk about that in a second. But like this number, this is an octal number, by the way, starting with a 0. That's a good choice for when you would like to make a file for open it for reading and writing. These are like default permissions that we'll get into. But you can like give 0, or it's just going to be ignored if you open the file for just reading. All right. So yeah, we're gonna say open at. We're gonna give a file name. We're gonna give a secret constant, the current working directory constant for that, and then yeah, we'll give the path name, and then we'll give 0 flags, and nothing else really matters. All right. So let's have the example finally. Let's make a file, and we're gonna open it with the open at syscall, and that will give us. By the way, what that does for us is it gives us a file descriptor. All right, that gives us a file descriptor that we can then read from. That int that we get back is a file descriptor that we can read from, right? Because read is taking this file descriptor. Isn't it? Nice. And then close, you eventually want to close your file too. You give it to the close syscall, all right? So we'll do all that together. Let's make a file first with some A's in it. All right, let's get that started. So what do we got? All right, well, here's a sentence. That's the special sentence that has every character of the alphabet in it. Quick brown fox jumps over the lazy dog. Hello world. No A's there. And then here's some lowercase a's. Here's some capital A's. Here's some alternating ones. I haven't decided if we want to count just lowercase a's or not yet. Maybe. Probably be easier. But yeah, there's a file. All right. And then now let us make a program that uses nothing but syscalls to do our stuff. All right, to read from things. Do I want to give it a main function though, just to make things easier? Yeah, let's use a main function at least. But we're going to read and write to file, or read from the file .txt for using just syscalls. All right, so let me copy in a folder or a file with an assembly main function, and let's figure out where this might be. Lecture 15? No. 14? Maybe. Haha. No, that was automatically generated. Darn. What else? Lecture 13? Nope. 12. I think lecture 12 is a good one. Pi.s, sure. Let's see if that's a good one with the main function. I will take it. All right, so let's copy that to here, and we'll call it count a's underscore syscalls .s. Yay. We're ready. So let's get rid of everything we were doing, and we'll still return 0 and all that fun stuff. But now I would like to count the a's, okay? And we're going to use syscalls to mess with stuff. All right. So first things first, I better open the file.txt file. Okay. So I need to make the open at syscall, which is syscall number 56. So that is going in x8. All right. So I want to open file.txt for reading. All right. And so that's x8, number 56. That's the number of the open at syscall. And then you could print this out. You can include this header and print it out yourself if you wanted to know, but it's if you search for drfd here, whee, This secret constant means your path will be relative, and that's what we want. You can make your own file and print out what that constant is. I did that ahead of time. It's apparently negative 100, all right? And that's an int, so W0 is where that goes, negative 100, and the negative 100 stands for this disgusting thing called at FDCWD, current working directory. So open, it means we want to open this file relative to current working directory. So where I am right now. So this lecture 16 folder. Cool. And then I gotta give the path name finally. This is the actual file name that I want to open. And that'll be file.txt because that's the name of it. And so I better put that in the data section, huh? Dun, dun, dun. Let's call it file name. And it's a C string. The Linux kernel loves C strings for a lot of things, and here's one place. So it's file.txt, and that's going to go in x1 because that's the 0, 1, right? 0, 1 argument. x1, and it's a pointer to this string. That is the name of the file. And then we would like to open it with flags. That's going in W2 because it's an int. Flags can just be 0 for read-only, or just want to open this file for read-only purposes. So move into W2 the number 0. So 0 is for read-only. And because we're opening the file just for reading, we don't care about this mode thing. That's only for writing when it's trying to create that file. All right, so let's make the syscall, svc0. Syscall is made, and so now we got an int back, in theory, if it did it successfully. We got an int back that is our file descriptor for the file, and now we can use that. That's the ID number. All right, so W0 holds, it now holds the file, the file descriptor for file.txt, assuming everything worked out, and it should have. Okay, cool. And now I want to keep reading from that file in like a loop, which is going to involve more syscalls with me messing with these scratch registers values. So this W0, I better save it away safely in a saved register. So let's use starting at 19, right? So moved up into W19 x0. So now it's safe. All right. So let's save that on the stack, and I think I'm going to need another one too. So let's subtract 32 from SP and just get ready to use another saved register because I think we'll need it anyway. So save x19 and SP plus 8. And then SP plus 16 can be x20. All right, remember that even though I'm using W19, that clobbers all of x19, so I better save the old version of it. All right. So we restore it here. Restore them both, and then it was 32 from SP. There we go. So yeah, now it's safe. It's W19 now holds the file descriptor. Cool. And then we want to keep track of how many A's, right? So now we want to read the file using the read syscall a bunch of times. We'll just read one character at a time into somewhere in memory. And yeah, we have to give the file descriptor there. And it gets to clobber our stuff. So all those scratch registers, just like normal function calls, syscalls do the same thing. They can clobber stuff, so we're saving the things we care about in safe places like W19, and I think we'll also use W20 for like the count of our A's, right? So let's count the number of A's. We need to save that number that's safe across function calls and syscalls. So what we want to do now is read the entire file, keeping track of how many A characters we see. All right, so let's save the count in W20. So I'll start off at 0. So now it's also safe across function calls and syscalls. Okay, we'll keep it there. And so I want to loop and just read the file continuously until I hit EOF. Okay, so I want to read one character at a time into somewhere in memory, right? The read syscall needed somewhere in memory. You gave the address of it here, and we'll just make space for one character in memory, won't we? That's all we need because we'll just be reading one at a time. Into, let's give a name for a place in the data section. Let's call it like next char, all right? And so just one character doesn't have to be a C string like we'll start off with an X and it'll get filled in. All right, so next char is the address in memory of a single character that we can mess with. All right, so in our loop, we want to read one character at a time into next char, and so let's use our read syscall. All right, let's make it happen. Let me steal a lot of this stuff because it's very similar, right? This is going to be x8, right? x8 is going to be the number of the syscall, of our read syscall, which is 63. All right, I got too many tabs open there. That's where I want to be. So read syscall is 63. And then we give, as the first argument, the file descriptor I would like to read from. That's going in W0 because it's an int, and it was W19 where I saved safely away that file descriptor. And then I give the address in memory that I want to write to as we're reading from the file. So I want to load into, it's going to be x1, the address of the next character, because we're just going to fill in the one character there. And then we say how many bytes we want to read. That's going to go in an X register because it's a wide number. I just want to read one byte. Read a single character at a time, please. So move into x2, the number 1, and that's my syscall, svc0. All right. So now, we get an answer back. This is how we know if we hit the end of the file or not. So we're getting back a size type thing. We're getting back the number of bytes that were read. All right. So let's see. Where is, here we go. On file, blah, 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 the file offset is incremented, blah, blah, blah. If the file offset is at or past the end of the file, no bytes are read, and read returns 0. So this return value, we can check it. So if it reads 0, then that means we hit the end of the file. Okay, that's the idea. So that's how you know. That's how you know if you hit the end of the file or not. All right. There's also like -1 could be returned if there's some sort of error, but if there was success, the number of bytes read is returned. So we're reading 1 byte. So we expect to see 1 back if it's successfully read. If we see something other than 1, like 0, that means the end of the file. Okay, so that's the idea. So 0 means the end of file. Where is that? That one. Okay, so that's what we'll check for. We can compare against either 1 or 0. Doesn't really matter. So if, here's kind of the idea. If what I just got back in x0, right? It's a big number. What read just returned to me was how many bytes it read, if it read any. So if it's greater than 0, then we successfully read another character. Otherwise, we're probably at the end of the file or there was some issue. So we'll just compare, right? Compare x0 against 0, and we'll branch if it's, what's the opposite of greater than, less than, or equal to? BLE, we're done reading. All right. Done. And so we'll put done reading down here. So we got more to do after reading, of course. So yeah, but if we're still here, if we fell through, that means next char got filled in. This next char piece got filled in from the syscall. It was an actual character that we just read, and we want to see if it's an A or not. All right. So star next char, essentially. If you dereference next char, give me that one character. It holds the next character, the one that we just read, and let's take a look at it. All right. So we got to get it somewhere. Let's get it in a register. So next char, let's get it in a register. So let's get its address. Let's dereference. Let's load a byte, right? Load a byte into W0 is fine. What's an X0? So remember that X0 holds the so X0 holds the address, and so W0 now holds the character itself. So what we just did is, like we said, W0 equals star next char, essentially. All right. And then now let's check and see if it was an A, because like remember our goal, right? So let's check and see how many A characters we found. This is the lowest level to do this. So let's compare W0 against the A character. And if it was equal to an A character, we want to add 1. And if it was not equal, we want to not add 1. So I like doing the opposite. All right, so if we fall through, that means we want to add 1 to count. And our count, remember, is being stored in W20. So we'll add 1 to W20 if we fall through. It was equal to an A, lowercase a. And then otherwise, we want to, if it was not an A, we don't want to add 1. It's not, sorry, not done add 1. Don't add 1. That's what I meant. All right, so if we don't add 1, we just want to, like, this should be then the end of the loop, right? So we want to keep on looping and try the next character. So just keep looping. Eventually we'll get here one way or another. So BAL loop. All right, so that's the loop. And then eventually we'll like hit the end of the file. We won't read anything extra. Read will tell us that that happened. And then we'll hit the done reading label. All right, so what do we want to do after we're done reading? Well, we want to close the file with the close syscall. We want to output the A's we saw. That was our hard work. We need to show that to somebody. Number of A's seen, and then of course let's return 0. And we're already doing that at least. All right, so let's close the file. That takes the file descriptor. That's all it takes, and it is syscall number 57. So move into X857. The file descriptor we placed in W19, remember? That's where we saved it this whole time, safely. And then that's it. Then we can make the syscall. All right. Oy, what else do I want to say? Dun dun dun. Oh, this needs to change. So read gives back a number in X0, and EOF is 0, error is -1. That's what I meant to say there. So we're going to read a character at a time. And I think I forgot to tell you that you should try some of this yourself. All right? It would be a good idea for you to like do some of this yourself, and I hope that you saw that and you tried it. But yeah, you can at least do the rest. So output number of A's seen. What do I want to do with that? That's just a printf call, right? So we're going to need a format string. The number of A's is in W20, so we'll print that with a format string. Format string number of A's colon %d new line. That sounds good to me. So we got X0 is the format string. W1 is the int we want to print, and that's W20, right? That's our count. Move that into W1. Then we can call printf, and all is well. All is right in the world now. And then yeah, we restore our LR, of course, because we called the function and syscalls and all that. And then X19 and 20 were also things that we use, so we had to save and restore them, and then we're ready to clean up the stack and return. So I think that's everything. Like just scrolling through this file, hopefully it all made enough sense, and that you got a little bit of it, even without me explaining it. So let's compile and run. See if it actually worked. Oh no, what have I done wrong? Let's see here. Dun, dun, dun. I did call it right, but it looks like on line 16 I did something weird. Oh, sorry. W0 needs to go into W19. That makes sense. I was like confused about the size. All right. And then on line 69, I forgot to say dot at the front there. There we go. I'm sure you've been yelling at me this whole time about those things. But now we can finally run our program, and apparently there are 7 lowercase a characters in this file. Is that true? I see how many? 1, 2, 3, 4, 5, yeah, 6, 7, if you don't count the uppercase ones. So cool, it worked, it did it, and it stopped eventually. It found the end of the file. So that's a great example of like the lowest level way to read and write to files. Okay, that's the idea. Write is exactly as you would expect. Okay, write is the same idea. It's just you're gonna open with a different mode now. You'll open with a special mode, and I'll talk about that. And it's everything that you've been using with like the, if you remember from the start of the class, like when you're doing the write syscall to just standard out. Okay, it's like takes the file descriptor, takes the string you want to write, and like how many bytes from that string you want to write to that file. Okay, so yeah, when you open a file with openat and you want to do it for writing, like you gotta, there's some flags that need to be set. So let's go to flags. So flags need to be like, we want to like create it. There needs to be like a write mode as well. It's somewhere. Dun, dun, dun. Yeah, probably that needs to be there because we want to create it. But then we need to give permissions as well, all right, to this file. So let's talk about file permissions, because that's what goes in the mode part. So here is a quick and dirty example of file permissions. So if we, let's use the, if I do ls-l, it'll show me that. Let's use file.txt as a guinea pig here. So when you do ls-l, it shows you a lot of about your files, and it shows you some of these things here, which are important. All right. So there's a lot of dashes on these lines, but they all mean something. They're all like a single bit worth of information. This first thing, it means read, W means write, X means execute, and then the dashes means that you don't have those privileges. All right. So file.txt is owned by me, my username. There's a group, there's always a group that your file belongs to as well. It's in the file belongs to the teacher group. And then you can have permissions for people in that group as well. And you can also have permissions for everybody else who's not this user and who's not in this group. Okay, so let's talk about that. So these RWs and dashes, they mean something. They're secretly encoding like a binary piece of information. All right, so file.txt, its permissions are as follows. There are, if it's a directory, there's something in this dash here, but everything after this is about files. There are 9 either characters or dashes. So let's talk about them. So the permissions for file.txt is, yes, it's readable by my current user, and it's writable. Read and write are the only things, the only bits that are set to 1. So that's a read bit, a write bit, and then it's 0 for the execute bit. All right, and then it's 0 for everybody else. All the dashes mean 0. All right, 0 is for everybody else. And let me explain. So these also mean read, write, execute. Read, write, execute permissions. And the first chunk of 3 has to do with the owner of the file. Owner of the file. So me, as the owner of the file, I am allowed to read file.txt, I'm allowed to write to it. I'm not allowed to run it like a program because it's just a text file. All right. This program that I compiled though, count as syscalls, that's executable by me, my user, and so that means it can actually be run. So the owner of the file has those permissions. The next bits have to do with the group that owns the file. By default, it's just nobody gets permissions other than the user, but you could set the group permissions to ones here. Group that owns the file. So that's how that works. And then you have everyone else. So these are the permissions that you give to everybody else who's not that user and who's not in the group. Can they read the file? Can they write to the file? Can they execute the file? And so, yeah, that's how that works. And because these are like chunks of 3 bits, 3 bits correspond to the numbers 0 through 7, and so this is a great use of octal numbers. All right, so that's why a lot of people like to talk about permissions in octal. So like this is 600 permissions, all right? And you can change them. So it's the chmod command that's going to do it for you. Whee! So look into that if you're interested. But let's like look at like ls. That's a program, right? Where does ls live? Oh no, that doesn't help me, does it? How about cd? Actually, cd probably doesn't help. What about pwd? That's built into the shell. Darn. Okay, let me just take my word for it. But a lot of programs that you run on your machine are in /bin. Okay, those are just like binary files. If I do ls-l, bin. Oh gosh, and it's a shortcut for user/bin. So let's go there. And here's a bunch of things, like the zip command, for example. It's owned by the root user, and the group is also for the root user, and so I'm none of those, and neither are you, but you can run the zip program, because here in these permissions you can read the file and you can execute it. All right, you're not allowed to write to it, but you have those permissions because it's a program that you can run. I can say zip or whatever, and it needed some extra stuff, but you kind of get the idea, I hope. So yeah, that's what file permissions are all about. And Octal is a great number system for that. And so you got to give permissions when you're opening a file that you plan on writing to. All right, so that's kind of how that works. That's going to go in the mode part. All right. So I just cut to where the actual description of mode is because it's way too hard to find it in the documentation. But here's what the mode argument means. That's where you give, if you say like I'm creating this file, then you give like what permissions you want to have here, and there are some constants that correspond to octal numbers, or you can just give the octal number yourself. So that's kind of how that works, and that's file permissions in a nutshell. So yeah, let's see. Let's talk about the C library, because that makes our life so much easier. All this stuff, we're slaving away, but honestly, standard.io.h gives you access to these syscalls in a much more sane way. Okay, you can open a file. There is just it's an fopen function. There's an fclose function. These are wrapping around the syscalls and making everything so much easier for us. So if you say fopen, you just give a string file name, and you give a string representing the mode in which you would like to open the file that has nothing to do. It's like the, oh gosh, it's the equivalent of flags, sadly. It has nothing to do with this. So people misuse these ideas, I think. But yeah, you got all these things. All right, you get back. Once you do that, you can open it in like read mode, write mode, read mode, write mode. I should select the right ones. Append mode, etc., etc. You can read the documentation, and you get back a file pointer. And this is just some type that's wrapping around a file descriptor. All right, so that's pretty cool. That's very useful. And all of these functions, fopen, fclose, fgetc gets a single character from a file. Like, let's go look at that. It's just everything is nice. Where is that? Get a single character, right? Lovely. All right, you can fread a bunch of characters, fwrite a bunch of things, rewind where you are in the file back to the start, or go to some weird place. So look at our Dive to Systems book for more information about it. But let's do what we just did, and we took so long doing. Let's do it with the C library. Let's just do plain old C first, and we'll go from there. All right. So yeah, here is the idea. We are going to open our file and count the A's in it again. So I'll make a new file and I'll call it, let's call it count A's .c. So I'll include standard.io.h and return 0, of course. And now let's use the C library to do all these things that took so long otherwise. All right, so I would like to say fopen. I like to fopen my file.txt in read mode, please. So you just give it R as a string. Oops. That's so nice. That's so nice. And what you get back is a file star. Where's that? You get back a file pointer. And so that's the type of thing I get back, file star. File star FP, file pointer is what we call it usually. And then you're off to the races. You can just keep reading from that FP thing. Let's keep track of our A's in an int variable, and then we just keep calling fgetc until we hit EOF. And if we're not sure what EOF is, where is fgetc? Give you back an int, the character that you got, or the EOF constant, and we don't know what that is, but we can print it out. It should usually be -1, like we've been using. EOF on this machine for the C standard library is %d. It's just a number. then I'll give EOF right here because it's a library constant, and we can just have it print out that library constant. CountaS.c-o CountaS. So it's a -1. Cool. Let us continue. So forever, I want to read files until I hit EOF. There is actually no true in C. So you have to say there's a constant somewhere, I think, called all caps true, if I remember right. But we'll just say while 1, because 1 is a true number. All right, so that's our while true in C. And I'll just get a character at a time as an int, though, because we might see -1. F get C from the file pointer. That's how you call it. That's how you use the library. And then, honestly, you don't even need to check against -1. You can just check against EOF, because that's a constant that's baked into the library. So if C is equal to EOF, bam, let's break out of this loop. Otherwise, we have a normal character. Let's check and see if that character was the A character. You can just compare an int to a char like that. It's fine. If it was, increment our A count, and that's pretty much it. We F open the file. We use F get C to get a bunch of characters. We can F close it. Gotta give the file pointer though. Now the file's closed, and then we can print out the number of A's. And that's A count. Isn't it nice to have high level languages? That's all you gotta do. Isn't it nice to have libraries? Beautiful. So, don't forget to close your files, but that's kind of how you use the C library to do cool things. And in theory, we will also see 7. Nice. Alright, so that's that one. And then let's do it in assembly, and I would like you to try this yourself. Alright, I have shown you the C program. You know how to use a C program. You know how to translate from C to assembly by now, hopefully. You're getting better at it slowly but surely, so give this a try. Give this a try, and then I'll show you how I go about doing my conversion. All right, it's just a bunch of BLs, right? And you'll have to make a loop with labels, but it's all possible. Okay? Dun, dun, dun. And then every time, let me try and explain like rewind and fseek and all that. Every time, remember, when you're like reading from a file, even with the syscalls, like here's your file. When you first open the file, it's like it puts a little character cursor right here. It hasn't read anything yet. And then after you read a character, it's moved the cursor so that it's ready like the next time to read the next character. That's kind of how it works when you read your file. You can say rewind to the file descriptor to say like go back to the start, please. I want to read the file all over again without closing it and reopening it. So that's what that does. And then fseek gives you fine-grained controls, like move the cursor to exactly here. Seek the cursor to there. That's like the technical term, I guess. So yeah, let's do this in assembly now. So I will keep this right there, and then I will steal, well, let's go to the syscalls one. I'll steal a main function from here at least, and then we'll call it CountaS, I guess libc is a good name for it. .s. Bam. So let's keep all these things. I want to do the same idea. Let's see. Honestly, these syscalls, they're just essentially getting replaced with library calls, aren't they? So let's think about this. All right. So I want to open file.txt for reading. What does that entail? Well, it's not a syscall anymore, so let's get rid of the syscall, and we'll deal with the rest later. But like, we need to eventually we need to BL f open, and so we need to give the name of the file. So that's going in x0. I called it file name, right? Yeah. Call it file name, and then I need to give the file, like the mode that I want to open the file in. And that is going to be, let's use this one. It's going to be a C string, and it will be the string R. That's the mode that I want to open the file in. So I'll put that in x1, and then f opens happy. And now I get back in x0 because it's a pointer to some file struct thing that wraps around a real file pointer, or a real file descriptor. So now x0 holds the file, not descriptor anymore, I guess file pointer, maybe, is what I want to say. It holds the file star. And that's a good way of saying it. And so let's move from x0 into x19, and now it's in a safe place again. So it's very similar to what we did before with the syscalls. It's just we're using function calls now. And so we're still doing that. And now we want to read a character at a time into next char. But honestly, I just want to read a character at a time, not into next char, because we're just going to get it back into a register, aren't we? So like we don't need next char anymore, and I already got rid of it down here anyway. So read one character at a time using the call to fgetc. Fgetc. So I'm going to say bl fgetc, and the file pointer is going in x0. So let's move from into x0 from x19, which is where I put the file pointer. All right. So there's that. Now I can call fgetc, and so now I have an answer in x0. That's the character. All right. So if x0, we know that it might be EOF, which is -1. So if x0 is not -1, we did not hit the end of the file. All right. So if x0 is not equal to -1, then we successfully write another character. Otherwise, we are definitely at the end of the file. Well, not probably. We are definitely at the end of the file. That's what it means. All right. So we'll compare x0 against -1. Oh, sorry. It's w0. W0. We're getting an int back. Excuse me. So compare w0 against -1. And if it's equal to -1, we're done reading. It's equal. Otherwise, we have a next character. W0 holds the character that we read now. So let's compare it against A. If it's not equal, don't add. If it is, we'll add. And then I think that's all good. Keep looping. We added one to account. When we're done reading, we want to close that file, and it's we give the file pointer, and then we blf close. So it's x0 gets the file pointer, which is an x19, cool, and then we'll blf close. And then we want to output the number of A's we saw, and so we can just use that format string all over again and return 0. I think that'll do it. So yeah, you see how we changed from syscalls to function calls. Library function calls, and that made things a little bit easier. Like this mode, we didn't have to deal with like a separate flags and then a mode command. It was just all very odd with the syscall. The library is taking care of that for us, so that's pretty cool. All right, so here's count A's libc.s. Count A's libc is what we'll call it, and I do believe we get the same answer. Beautiful. All right, so yeah, that is just a wrapper, honestly. All this stuff, the C library stuff, is a wrapper around the syscalls, but it's less to think about in your brain. So that's why we use them. And you can imagine that the same thing's going on in C++, right? At the end of the day, everybody's going down into read and write syscalls and open at syscalls and close syscalls and all that fun stuff. So even fstream, you're using fstream in C++. You're opening a file, you're getting a character at a time with methods now. You know that eventually it's making its way down into syscalls. It's making your life easier. All right? So yeah, I think that's what I wanted to say for today. We've learned a bit more about files. We've got more practice with it. All right? So let me release your next homework now. This will be a multi-week homework, so definitely start early. And let's take a look. All right? So mine's the due date, but this one's going to be about caching. All right? So here are some tables on these pages. You're going to fill out the tables. Right? So let's pretend that our program, just like those crushed ices, just like the in-class exercises from the caching lecture, let's pretend that our program wants to read the following memory addresses in order. And these are decimal addresses, not hex ones. These exact addresses, 41, then 37, then 49. All right? And let's assume that we have a cache. We're going to explore different kinds, but our cache, whatever kind it is, it holds 8 blocks total. All right? And just like we were doing in the in-class exercise, let's just pretend that every data block is a single byte wide in our cache. All right? So you can only hold not a chunk of things, just one single byte address in each line of our cache. And then we have a bunch of tables. What I'd like you to do is, using these tables, I've started out the cache holding some addresses right now. They're not blank like they were in our class exercises. So they got some stuff in there right now, but that might not be what we want. So using these addresses, read from them and see how that affects a direct mapped cache, a two-way set associative cache, a fully associative cache. All right? So yeah, simulate the cache behavior for these different kinds of caches. All right, they've got those initial addresses in the cache already. It's holding some things. It's caching some things already. And what I want you to do is assume that if you ever have to, if you're ever doing LRU replacement, and I do want you to use LRU replacement for the associative ones, assume that the lower line numbers were filled before the higher ones. So line 0, that's older than line 1. All right, line 0 is older than line 1. Same with these. Line 0 is older than line 1, line 1 is older than line 2, all the way to line 6 is older than line 7. Think of that as the age of these guys when you're doing your replacement strategies. And then remember how you're going to figure out which line you're going to look at. So for direct mapped, you're going to just do mod 8 essentially. For your associative caching, you're going to do mod number of sets. And for your associative caching, I want you to use the beautiful LRU least recently used replacement strategy that we talked about and we did examples of. All right. So as you're filling these tables out, I want to see your scratch work. All right. I want to see your scratch work just like I was doing in class. Don't delete, don't erase, but cross out what used to be there. All right. And then that'll actually help you because I also want you to calculate how many cache hits were there and how many cache misses were there. You know that there's going to be as many misses as you crossed out, right? So that's a helpful thing. So that's pretty nice. And so I think that's all that I wanted to say. So for read all these addresses, you're going to get some hits and some misses. Keep track of them. For a direct map cache that only has 1 byte per line. And then do the same for a two-way set associative cache with LRU replacement. And then a fully associative pie in the sky. This is never happening in a real CPU cache. But it's pretty nice. If only we could do this. All right, this is the one you want to compare your actual strategies against. All right, so keep track of that. Fully associative, so anybody can go anywhere, but with LRU replacement. All right, so that'll be your homework 3. Let me know if you have any questions about that, and I will see you in the next one.